Hello, welcome to Washington Post Live. My name is Joel Achenbach. I'm a science reporter here at the Washington Post, and I am really excited about today because we are going to be talking about the James Webb Space Telescope, which made an amazing splash last week with the release of the first set of images taken by the telescope, which is out there about roughly a million miles from Earth, looking at the cosmos at multiple layers, including pretty much all the way back to near the beginning of time itself. So we have as our guest today, I'm delighted to say, Dr. Thomas Zurbuchen, who is the head of science at NASA and in charge not only of the Webb in that program, but of many other programs to come. And we're going to discuss, I think, mostly the Webb today, Dr. Zurbuchen, but also feel free to tell us what else NASA has coming along. So welcome to Washington Post Live.
I'm so excited to be here with you. Thank you so much.
So it's okay if I call you Dr. Z. I know people call you Dr. Z. You can call me Mr. A. We'll go to A to Z. I hope
Yeah,
that's
that's
okay.
absolutely great. Absolutely calls me that. Yeah, absolutely. Either that or Thomas. Either way, it's just fine.
Okay. Um, well, I'm going to start with not even a question, but really just an exclamation, which is wow. I mean, as a science reporter, this was a really exciting story, and I think for everyone across the planet to see those images. When you and I talked last fall, you were very open about that you were nervous because there were so many things that could go wrong with the mission, and it was just, natural to be nervous. How are you feeling now?
Oh, I'm so relieved, and of course, enormously proud of the team that got us there. I was rightly nervous. It's not the case that I was like I'm a very nervous person, generally speaking. I do many things kind of that are challenging, and that's kind of my job, both here at NASA, but I've always been that way. But this is the most complex mission we've ever done. There's 1,000 ways or more that this could go badly, and one way it can go well, and that's the way this team chartered, right? And so for me, it's just very excited for them, proud of them, but curious about what we're going to find now.
Just for a second, can you summarize why there were so many things that could go wrong? Obviously it's the biggest, most complex space telescope, but without going through all 344 single point failures, just tell the audience, why this is so difficult.
So Joel, first of all, let's just look at the size of the team. It was interesting. I was in this week. I was in Athens, and I went and had a tour of the Acropolis, and they basically talked about the size of the team that built that historic monument. The answer was 20,000 people. That's the number of people that build the James Webb Space Telescope. So it's a really historically big team. When you have a team like that, it's really, really hard to do. So that's the first thing you need to recognize, especially because of the fact that these has three space agencies, in many different countries, many states in the US, and so forth. In addition to that, it's a very complex, frankly, mechanical system. So it needs to run really, really cold, and it needs to be very, very big. Those two things together, having to launch, of course, in a rocket, it has to fit in at the top of a rocket, makes it enormously hard. It's almost like a transformer of a spacecraft in which you launch something that is shaped one way, and you saw it in the little movie up front, kind of like a little package, and then it folds up into something at the bottom that is the size of a tennis court, right? That sun shield that keeps the telescope cold. The telescope, of course, being 21 feet across, which is much, much bigger than any other telescope we've ever done. The Hubble was only 2.4 meter, kind of a third or so of what Webb is.
Well, and also it has to operate out at L2, which is roughly a million miles from Earth, and you can't send astronauts out there to give it a kick if that sun shield doesn't open up. So, so what did you think when you realized that it worked, and when did you realize this thing really does work? And what did you think when you saw those first amazing images? What was your reaction?
So the first key milestone where of course, by the way, I always hoped and believed it would work, right? I mean, you the most important thing we have in our work, besides building the best team we can equip to really do this work, is the hope for success. We always bet on success. I mean, I never bet on failure. I had no contingency plan, right? It's like this has to work. Same is true, by the way, when we landed on Mars, the February last year. Like it has to work, and frankly, we built the follow-up mission assuming that it will work. We had no other contingency plan, and so we're always going to do that. So when I first time I really felt enormously relieved. It's kind of something like 7-8 days after, when the whole sun shield was deployed. For me, if you just look at it in terms of complexity, the pulley system, that kind of tennis court sized 5-layer sun shield, once it was deployed, I'm like, wow, this has, we're a long way there. And I was there for the last deployment of the side, one of the three mirror sides of the entire mirror that had to be deployed. And then, of course, once the first images came out, right, there's really two things.
Yeah, Dr. Z, tell us about the images. Tell us about the images, Dr. Z, if you can. What did you think?
Yeah, I saw the images coming out, and it took my breath away, frankly, initially, because it's incredibly beautiful. And so it's both the amazement of the images, looking at them, but then their beauty of the universe, how beautiful it is, how complex it is, but also the pride of the team that got us there.
Right. So the engineering that went into this mission, we've just discussed it. It was amazing, a tremendous feat for NASA and its partners in Europe and Canada and all the contractors. But talk about the science. What is this telescope going to do? What are we going to see out there? And really just describe what's coming up in the next, hopefully, many years of observing the universe.
So first of all, the telescope was built to really look at the universe in its very coldest light, the infrared light. So it's kind of, if you said, if you have IR, on Earth, how would that feel? Well, it's more like a sensation on your skin, right? So the eye doesn't actually see it. So it's very, it's kind of a signal of heat, so to say, that's coming. Now you say, why does that matter? Well, there's at least 3 reasons you want to see that. First of all, the old universe, because of the expansion of the universe and kind of the kind of moving of the farthest reaches of the universe to colder and colder light. For that reason, we want to look back in time. So that's the number one reason we wanted to do that. That was what motivated the scientists even 25 years ago. The second reason, of course, is when you look at the universe in that light, you see kind of chemistry, kind of the molecules that we're breathing out, whether it's CO2 or others, they oscillate and emit radiation in that wavelength range. And the third one is that if you look at infrared, and of course the military is using that, we're using that when we search for people, kind of we can see through, for example, the fog, we can see through dust and look what's behind, looking at the heat signatures. And those 3 reasons make it an enormously powerful tool, never precedented.
Describe just for a second what that big mirror gives us in the way of resolution. I mean, obviously, other telescopes have looked at the universe in the infrared, like the Spitzer Space Telescope, and even the Hubble goes a little bit into the infrared, even though it's mostly in the optical part of the spectrum. But what about the design of the telescope that allows you to see things that other telescopes could not have seen as well?
So if you looked at Hubble and Webb at the same wavelength, right, and basically looked at the resolution it has, kind of the parcel in the sky, it can really resolve kind of with clarity. Basically what happens is Webb is basically largely a third better, just based on size, but that would totally understate it, because in addition to that, it's cold. So basically what it means is actually that parcel, if you looked at it for 1 hour on Webb and 1 hour on Hubble, the Webb would give you something like 10 times or 20 times, depending on the noise signatures, more clarity. And so basically it's both and the third piece is you have collection area that is also more, so kind of so there's 3 things that go in the same direction. So higher resolution in angle by a factor of 3, but much more collection area and less noise in the system, which makes it so much more clear. All these things matter and give us a kind of a sensation of probably 10x or so more kind of power in a given picture. Of course, you have to make this scientific and argue about it, but that's the way I would think about it.
When I was at NASA last week for the big release, when you were there, one of the engineers said that the Webb is performing so well and so far beyond spec that it should be able to see first light. And I think what he meant by that was not the microwave background radiation, which is really the first light, but the first stars and galaxies. I've heard other scientists say, maybe not. It's tough out there beyond redshift 11 or whatever it is. Can you explain that to us? How far back in time and deep in space can this telescope potentially go?
Yeah, so let's just talk about timescale, kind of the beginning of the universe, and of course John Matter and Reese and others got the Nobel Prize for that. Is 13.8 billion years. That's the beginning of time, kind of the Big Bang, and where the galaxies arise, frankly, is a matter of debate, right? So some people say it's 100 million years later or 300 million years later. So what we announced last week is that even in the first image, we had light already from 13.1 billion years, which 700 million years after the Big Bang. I don't know what you've seen, Joel, but there's in the archive, there's a first result already submitted as a paper, which is 300 million years. So it's already halfway closer to that initial point. So it's kind of, and the question really is, frankly, there are two questions, like when are the first galaxies and stars? Is it closer to 100 or 300? And will we see them? And for me, the first question is frankly the more relevant one, because we seem to be getting so close already. This is a week into it, Joe. We're already kind of having, of course, results that need to be confirmed through peer review, but are already telling us we're getting as close as many scientists thought the first galaxies are. So I believe we're going to get awfully close, if not really, getting to the first ones.
Thank you. We're going to go to a question from the audience here. This is Johanna from Pennsylvania, who asks, what is the most ambitious goal of JWST? What is its life expectancy? How often should we be seeing data and images?
So I think the most ambitious goals, there's really two. The first one we just talked about, which is to really image the first galaxies in the universe, which is kind of the earliest page of our picture book of life, right? Kind of out there after the Big Bang, when big elements that were built out of form in these galaxies. The other one has to do with really finding planets in our own galaxy that could harbor life. For me, that's an equally ambitious goal, and a goal that's a lot more modern in time, because frankly, when Webb was started, that was not a goal that was there. We'll have the way we talk about the lifetime of Webb, there's kind of two ways to talk about it. The first one is design life. So everything was tested that it surely will work for 5 years. But then there's a number of things that need to all work together to basically say how much life we have. And a lot of that we're still figuring out. The fuel lifetime, because of the excellent launch that Arianespace gave us, is at 20 years. But there's other lifetimes that matter. You heard about the micrometeoroid that hit us, right? Kind of that rate also matters, as do other, like the lifetime of the cryocoolers, in subsystems. So I would say between 5 and 20 years, and if we're lucky, even beyond that. And then how often do we see images? All the time. You should be waiting for almost weekly, bi-weekly, you see new images.
Well, you actually just mentioned something. No, I had not checked the archive. I did not realize that someone had posted a paper showing, was it a galaxy 300 million years after the Big Bang? Is that a galaxy?
Exactly right. Exactly right. They found one that has the spectral signatures of that kind of galaxy. And again, that needs to be confirmed through peer review. But my point is, from the beginning, when we announced 3.1 billion, I'm like, this is good. We're going to see this record shattered. This would be the oldest galaxy ever observed by any means.
The one that just posted that
exactly right.
Okay, so that's a new record. So that's amazing. One thing that you're pointing out that may not be obvious to everyone is that the data are going onto a public site, right? So if I'm a graduate student in someplace far away, I can work with that and potentially publish findings about it. Isn't that true?
Exactly right. A significant fraction of the early data we want to put out right away for two reasons. For the reasons you said, frankly, we want citizens from around the world to who are interested in science to pick up those data and play with them. I think it's just amazing. We already see charts that people put out because they do so, people who are not astronomers. And then we also want the astronomy community to know what this telescope can do. And we want them to recalibrate their expectations. We want them to be more ambitious. And so for us, that's absolutely critical that is happening. So really take full advantage of this new capability.
When you say be more ambitious, are you implying that maybe a lot of people didn't think it was going to work? The sun shield wouldn't open up, the mirrors wouldn't open up, and that they may have calibrated their ambitions according to some pessimism that the Webb would be able to produce at the level it's producing. Is that what you're saying?
Many of them, of course, thought the telescope would work. That's why they said, I want to use it. But what they had said, for example, for a given, exoplanet, I need 10 hours of integration to resolve that exoplanet. What we found in some of our initial data, it only took a third of the time because the telescope is overperforming. So they could do 3 exoplanets instead of 1 for that time. So for us, it's really leaning forward into it and use the capability as best as you can.
You mentioned a minute ago the I can't say it, the micrometeoroid.
Yeah, you
I
got it.
can't spell it and I can't say it. Impact that happened in late May. Can you explain to the audience, what exactly that meant? I understand it did some damage that cannot be entirely fixed, but did not throw the telescope so far out of whack that it made a huge difference. But the concern, as I understand it, is that the model for the amount of dust that's out there at L2 may have been imprecise, and because you were expecting this kind of thing to happen maybe once every 5 years, and in the first 5 months you get hit pretty hard. So was the model wrong?
Yeah, exactly right. So one of the things we're always reminded by is that space is not empty. So it's full of these plasmas, the gases from the sun. And of course, the telescope is designed to handle that, but it also has dust in it. Part of it are these little grains, and they're tiny little dust grains. And we've been hit 6 times already. We expected to be hit every month or so with one of them, but a really tiny one. And there was this bigger one that came, and you just mentioned it, that came too early. And it makes us nervous, right? And so think of it like, if I was into cars and I bought this amazing new car and it's shiny, it came from the dealership, and somebody smacked the door into my side, so there's a dent in my car. Well, it's still a car, but there's a dent in it. So the way I think about it is that we need to understand what how abundant these these heavier hits are going to be, or even heavier than the one that hit us, and just say, hey, can we do something to protect the telescope more than we are right now? For example, by if you want flying back first into the dust streams where we know that most of the dust is coming from. So that's what the team is working on right now.
Let me ask you about the name of the telescope. Obviously, there's been controversy about the name, being named after James Webb, the former NASA administrator during the heyday of the Apollo era. That there has been concern that he was complicit in the repression of the rights of gay and lesbian federal workers back in the 1950s and 1960s. And we heard last week that NASA is still looking at that and is planning to issue some kind of additional report on it. Can you discuss that? When will we see this report? Will it be renamed? And how do you feel about that?
Well, so first of all, the most important thing I feel about is that gay and lesbian scientists are welcome to work with Webb and our data and our teams, as are everybody else. That's the standard that I want to set, both as a leader at NASA, but and by the way, that's not just for that group; it's also for our colleagues who might be immigrants, people who are, communities that are not generally have been part of our community. It's absolutely important for us that they're there. It is true that NASA is still working as the archives have opened and basically looked at this and has been working at really seeing where there's something there. This is handled at the administrator's office, and we'll see what's coming out of there as we go forward. Personally, that what I'm focusing on, and much more than anything else, is what I started with here: is we want to build an environment in NASA, all NASA science programs, not just this one, where everybody's very much welcomed and basically feels that they are kind of at home and kind of can contribute to these amazing missions that we have.
So will you contribute to that decision one way or the other? Will you lend your voice to it?
I've been engaged in a number of discussions. At the end, the decision is not handled by me.
Gotcha. I want to go to another question from the audience. This is from Mary Ann from Pennsylvania, who asks, how will all the money spent on space exploration help our planet? And this is a question that I think a lot of people ask, which is, we not only with things like the Webb or the Perseverance rover that landed on Mars and other space science things, but also questions about human exploration and going back to the moon. But talk about the astronomy. Why is this important to people on our planet?
Look, it's important for two reasons. The first one is the technologies that we're developing here. And so often, many of these technologies have imminent applications both here on Earth or in space to look at Earth. This morning, as we woke up, we looked at weather forecasts that benefit from technologies that were developed for previous telescopes that are looking at the Earth, imaging it with different wave bands, including red wave bands. And the technologies that we're developing surely is advancing that kind of ability and giving us more data. Technologies also have very unexpected benefits sometimes, in our own phones that we're carrying around. This technology that initially was designed elsewhere. So that's really that kind of application space really, really matters, and especially as it focuses on our planet, matters in an existential fashion. It's also true, though, that I believe that countries like the United States, have benefited from doing both, kind of dealing with the issues of today, but also looking at inspiration of tomorrow and kind of pushing the boundaries. Pushing the boundaries has served as well, because problems that we don't yet have today, we're finding solutions to by doing research today into the tomorrow. So for me, that kind of aspirational and inspirational part has always been part of the United States, and I surely believe and hope it will be in the future.
Let's talk about money at the level that you have to deal with, figuring out which missions are going to get how many dollars, because there's a lot of proposals out there and big dreams for new telescopes and telescopes that can directly see planets in a way that even the Webb can't. The Webb got labeled as the telescope that ate astronomy. I forget what journal said that, but it did cost a lot of money. And I know that there are people who would say, hey, it's worth it. It's spectacular. But are you concerned at all about how much Webb cost? And I guess from a practical standpoint, how can you make sure that you don't have a mission that gobbles up all the money that could go to other missions?
So I'm deeply concerned. First of all, I'm a taxpayer. I want the money that I'm giving the government to be spent in a responsible fashion. I want performance of the money that's coming from me, whether I'm in charge of the science program or somebody else is, to be done with the same kind of attention that I expect when I spend money on somebody else, whether it's the car dealer or somebody else. I expect performance. And frankly, that's what the job is of our team here, is to do the best job possible in building that. Now, it's a lot easier to build, the 100,000th car after you did the others than a first of a kind. And so, kind of what we're doing when we're pushing the envelope, it's just harder. And but everybody says, well, it's worth it, and people will forget about this. I told my entire team, we will not forget the lessons that we learned, and some of the challenging chapters of this telescope we will use for every mission that we're doing from now on going forward. That's our job.
Do you think the telescope will help us understand life beyond Earth? Obviously it can take the spectra of exoplanets, but it wasn't designed for that mission, as I understand it. In fact, it was sort of designed before we had really discovered thousands of exoplanets around distant stars. So, but the whole issue of life beyond Earth is important to people. They think about it all the time. How will the Webb help us understand that?
So life beyond Earth is one of the top topics in all of the NASA science program. We have many different missions and we're spending billions of dollars on that because it's such an important question and so much of interest to our citizens in the United States and beyond. What Webb will do, of course, it will measure, atmospheric signatures of these planets in our own galaxy. And of course, you say, well, does that matter? Well, look at the Earth when life was arising on the Earth, kind of single cell organisms, the entire atmosphere changed. And what we're really excited about is looking at atmospheres and looking at signatures that we believe has to do with habitable planets, kind of signatures of even, places where life could arise that shift the atmosphere into things that have more CO2, for example, things that coming out of our mouth that is, a product of life, or N2, nitrogen, and so forth, which we also believe has a lot to do with life by many theories. So yes, we seek to learn. Kind of searching for life elsewhere is not a yes/no question. It's a whole set of investigations that together help us to understand how scarce life really is in the universe and how it evolves from kind of a chemical type of environment of stars and stellar regions and planets to something that is truly alive.
So look, we have time for, I think, one more question. This is one that is from our audience. It's from William from California. He says, do you personally believe that humanity will figure out the physics of how to travel across interstellar space? So warp drive, etc. Is that something that we will figure out one of these days?
I sure hope so, because I mean, for me, if you ask me what's the mission you would really like to do, you're not working on right now, it's making progress towards travel to the next star. I mean, for me, Voyager is out there a couple hundred, nearly a couple of hundred times the Earth's sun distance, and yeah, I'd like to go to 1,000 or 10, kind of 10x more at the same at the same time or so, to kind of to learn how to do that. And there will be progress that come from propulsion and other technologies, including perhaps the geometry itself of space itself, which we don't know yet. And I sure hope we're going to do that. For me, when I hear big questions like that, the answer is never no. It's just I don't know when.
Dr. Z, this has been really enjoyable. We're out of time. Thank you so much for joining us.
Really appreciate it, Joel. Really appreciate it.
And thank you, the audience, for being here today. If you want to see other programs that are coming up, go to WashingtonPostLive.com and see what's coming up next. I'm Joel Achenbach. Thank you so much for joining us.